All right. Thank you guys for showing up for week 3. Hope you guys enjoyed the presentation last week by Jack and Kiro. As for this week, we're going to be covering some more stuff related to applications in the industry. Starting off with Ethereum being the first smart contract platform that released in 2014 and being arguably the most influential and the most impactful blockchain today. After I give an introduction on how Ethereum basically works, I'm going to kick it over to Kiro, who will be presenting on some stuff related to the current industry, decentralized finance, and a cool paper he wrote on the stability of stablecoins. So it should be a relatively pretty dense meeting, but also pretty quick. Feel free to raise questions or raise your hand if you have any questions at any point. But we're going to try to give you this knowledge as a background to a lot of the industry work that's being done today, specifically with trading, investments, building new platforms, new protocols, etc. So this should give you a lot of context on what people are talking about on Twitter, what people are building companies for, etc. Yeah, cool. So to start off with Ethereum, and we covered this briefly week 1, but it's a smart contract platform that was released in 2014 as sort of the second major cryptocurrency that got adoption. That was different from the first major cryptocurrency that got adoption in terms of the smart contract platform functionality. Previously, between 2009 and 2014, there were a lot of sort of forks of Bitcoin. I'm sure you guys have heard of Litecoin, Dogecoin, etc. They essentially have the same mechanisms as Bitcoin, but they're just branded a bit differently and sometimes have a bit of different parameters related to the mechanism of sending currency outputs back and forth. So with Ethereum, we kind of step into a new area. This is more of trying to create abstract logic on the blockchain. In other words, trying to create something that's programmable that will allow it to stay on the blockchain forever and allow it to be decentralized in that anyone can access it and call functions at any time, given they have the permissions written into the logic. And so to take a step sort of higher level on this, Ethereum itself is essentially a state replication machine. The purpose of it is to replicate the state of the Ethereum sort of network or the Ethereum state as a computer across every node in the network, and by proxy, every sort of user or person who's connected to the Ethereum network. In other words, if person A and person B are in 2 different settings, they should, if the protocol is working properly, be seeing the same set of transactions, same database, same storage throughout the whole blockchain. This makes it really convenient to be doing sort of cross-border or sort of internet native transactions that are not limited by other things, but only by your ability to connect to the internet and run the program itself. So it's a very computer first way of looking at things across the network and trying to get people on the same state. When people make transactions, of course, the state has to be updated, which we will cover now. So when people make a transaction on the blockchain in order to move some money around and move some tokens around, mint a new NFT or anything of that sort, the transactions are fit into a block, and the block is the thing that's being added to the network. These blocks are the things that make up the blockchain, and from its name, they are sequenced one after another with cryptographic mechanisms that we covered last week that basically have each block pointing to the one previous to it. This results in this global history. The idea is that because each block is dependent on the block before it to be added into the blockchain, there is no sort of argument on what's the history of things, since they all point one backwards, and they basically all have a previous block that determines where they sit in the history of all the blocks. The state transition function we look at Ethereum, again, this is sort of an abstracted template of it, but the state transition function we look at is one that the chain itself, being a network, has a current state and then takes in a new block, and as long as the transactions that run on in the block itself are completely valid according to the network rules, the block is accepted by the node, and then it is broadcasted to the rest of the network, and the state transition function is completed. This is the actual sort of innards for the blocks themselves, and also the transactions. So they're actually deceptively simple. For those of you who kind of have been looking into blockchain and looking at sort of the terms, and specifically in Ethereum with a lot of like the words that are being used, this is the raw data structures or the basic data structures they all come from. Here on the right side, we have the struct of transactions. This is basically telling you what the data structure of a transaction is laid out. You have all these fields on the left-hand side, the field names, and then you have the field types on the right-hand side. So U64 stands for unsigned integer, 64 bits. You can follow for the rest of the logic. You can look at data, which is a vector of integers, which is actually a bit more important because the data is actually used as the bytecode that's run on the Ethereum Virtual Machine. In other words, the data is the sort of code that is processing transaction or the instruction set for the transactions themselves. The rest is sort of other logic and specifiers telling the EVM what exactly to do with the transaction. For a brief run over of the fields, the nonce is something that's quite unique and quite, I would say, clever that the designers of Ethereum made. The idea is that each account can only have one nonce per transaction, or one transaction per nonce. So the idea is that you start off with an address, or like you start off with an address, which is your account. They're used interchangeably, the names. And you start off with nonce 0, and when you send your first transaction, you put the nonce as 0. And then if anyone else comes along and says, and say perhaps has a valid transaction that you did, but it was on another chain because you used the same private keys or something of that sort, they wouldn't be able to actually replay that transaction or rebroadcast your transaction onto the Ethereum chain, because if you signed your transactions with nonce 0, and they get confirmed by the network will not accept any other transaction from that account with nonce 0. Nonce being number used once, it has a different context in Bitcoin, but here it's about accounts actually making transactions themselves. The next two fields are gas price and gas limit. These essentially are the way that transactions are priced and monitored. So gas is a fundamental unit of computation in Ethereum. The idea here being that the state replication machine or the piece of software is being run across the network, and to run the actual transactions requires real work at the bit layer or the atom level, because what you're doing is you're just flipping bits on computers around the world, and these things take time, and they also take storage, right? Those are your two basic resources. The Ethereum network prices operations in terms of the gas, and the pricing basically comes down to how much time would this take in terms of work, and then how much storage would this take in terms of storing data on a computer across the network. So all your transactions are priced in gas. The relatively simple ones are pretty cheap, such as just transferring Ether or ERC20 tokens back and forth. They're pretty low gas. The higher, more complex transactions that have more logic cost more, and which is why you will see some transactions, or some people say they've paid hundreds or thousands of dollars for transactions at times when the price, when the network is congested and the price of gas is very high. The to field is just an address. It's basically saying where are you directing this transaction at, and we'll get that more into that in a few slides. The value is how much Ether you're sending along with the transaction. So the value is just specifying the Ether value of the transaction. And if you're dealing with other tokens, this value would be 0. And the data, as I mentioned previously, is for the code, or the actual inputs of the instructions the transaction is submitting. And then the last three fields are just cryptographic signatures. The block itself is the main abstraction here, again, or one of the main abstractions. And the block has two fields, one being the header and second being the transactions. So the transactions, those are pretty simple. It's just a vector, or you can think of it as like a store. It's just it's a vector. It's like an array or a list or whatever you like to think about as a thing that contains it. But it's just a vector of transactions that are ordered, and it has one transaction after another. And it has the block header, and the block header is another field that contains the canonical properties of the block itself. So it's basically just block metadata, when the block was mined, like the address of the miner who mined the block, how much how much Ether the block itself was paid out to the miner as a result of the successful mining of the block, and also the previous block's header, just to chain it to the global history. So these two data structures are your primary sort of concepts when it comes to actual blockchains. And through this, we can already start seeing that we're getting actually a lot of sort of room to play with here, because with this, you have a lot of sort of ability to create a virtual machine around it, such that it can execute arbitrary code, but also be cryptographically secured, allow users to make transactions and hold money through their public and private keys, and also create a global history of blocks where each one is verifiable to the one before it, and also tells you which transactions are in there. This is just a diagram of how the accounts actually work. I mentioned addresses. You can think of them as accounts. So the names accounts and addresses are used interchangeably in Ethereum. They're the same topic, but they're just a different way of looking at things. The address is the actual 40-byte field, a 40-character field of the sort of name of that account. The idea here being that it's sort of like a public, it's like a public key essentially. Another sort of way of looking at it is it's like an email address. So your address is basically your email address of the chain. It's not something you choose yourself. It's just a random hexadecimal string that's, well, not, it's deterministically generated through cryptography. So you own the private and public keys that associate with an address. Then your account is actually one of two things. Accounts in general are either externally owned accounts, which are people who actually themselves hold the public and private keys, or they are actually what's called contract accounts. And this is one of the main things that Ethereum really kind of focuses on, is the idea of code running independent of humans and is in a decentralized manner as the network processes the transactions. Smart contracts themselves can be accounts, and smart contracts being accounts would have code deployed at their address. As a result, you can have logic being stored on the blockchain that runs as a function of inputs or other transactions from other users. In other words, an externally owned account on the top diagram here can create a transaction that calls a contract account, and then in the contract account, it itself has code. So the instruction memory or the sort of input data would be coming from the first transaction. It would hit the second account here, being the contract account, and the contract account would have logic or code deployed as bytecode at that address on the blockchain. And then the miners or the nodes, when they process this transaction, would be actually running the logic or the actual instructions of the first transaction into the code of the second account. If the account itself has logic that calls other contracts, it's creating what's known as an internal transaction, which is essentially just a sort of, you can think of it as another process that calls another contract account and goes on and so on and so forth. It's just basically internal calls that make function calls to other code located at other addresses. But the importance of this diagram here is to show you that all transactions must start off with one person being the originator, or one externally owned account being the originator, and everything else is a result of code execution. The second diagram here on the bottom shows the sort of basic transactions here, which are just from one EOA to another EOA. This most simplest example of this would just be sending Ether from one address to another. You would just the transaction is just sending, so it would decrement the balance of one account and increment the balance of another account's Ether value. So this is the basic idea of the account value model, or the account model that's present in Ethereum. That also is a different design than the one that's done in Bitcoin. So these transactions, to focus on them for a second, they're atomic operations. What I mean by that is that the transaction fully executes by itself in its own timeline. In other words, when a transaction begins in Ethereum, that's the only thing that's running at that part of the state's history, of the blockchain's history. And then once the transaction is complete, anything else can happen after it. But for the time during, there's nothing else that can interrupt it. There's no context switching. For those of you guys who've done some operative CS, there's no other, there's no like, they don't have like mutexes or locks or anything. They're just basically everything, the execution state happens at that transaction fully and then moves on. But these transactions are also order dependent. So transactions do run one after another. And as a result, order actually does matter here, because depending on where your transaction is actually sitting in the block depends on the it can change the execution of your transaction. If you run some code that depends on a state of a contract somewhere that someone updated before you. And this is one other thing that's sort of unique about the blockchain, is that the values at read time, or the values at read time don't necessarily actually correspond with the values at write time. What I mean by that is that if you're looking at the network in a normal setting and you decide to create a transaction saying sending or making a trade on a platform that's that is a smart contract, when the actual transaction gets broadcasted and confirmed by the network versus when you actually create the transaction has some sort of propagation delay. One being the actual propagation delay across the network, but also two, the delay in the transaction waiting to be confirmed by a miner being put into the block. Just to make this clear, there's two sources of delay here. One is physical network delay from the transaction being broadcasted across the network and gossiped to other miners. And two is actually the delay of the transaction sitting in the miner's memory, waiting for the miner itself to win the mining puzzle and be included in the block. In the second sort of delay, we call this the transaction sitting in the mempool. The mempool is just a set of pending transactions, and each node has its own mempool. And as transactions come into one node's mempool, it makes the most sense for them to gossip it and share it to others, because for miners, they want to be mining on the most recent chain. So they want to have the most up-to-date information. And they also want everyone else to be mining on the same version of the chain as they are, so as not to get sort of erased from the history of the blockchain. And that's more of a consensus thing, but yeah. And one other thing about transactions is that these transactions themselves, if they fail, which is possible, right? Because there's delay between when you actually create a transaction and checking if it's valid to when the transaction actually executes. If the transaction fails and it's also included into the block, the failure will just occur and no actual state change will occur except for the user paying for that transaction. So in other words, failed transactions can actually still be included in the block. They're just a result of you either purposefully creating a failed transaction or you creating a transaction that depends on some logic that becomes false when the transaction is actually added into the block. This is again just more details on the sort of execution environment of the Ethereum blockchain. Sort of also as a kind of a general sense, a lot of other blockchains have adopted the Ethereum Virtual Machines model. So actually these terms are kind of generalizable to a lot of the other more popular blockchains, with the exceptions of ones that create their own virtual machines and execution environments. So alternatives to Ethereum's EVM would be something like Solana, or Sui or Aptos, some of the newer ones. Blockchains that actually have this sort of execution environment with the same exact settings would be something like Binance Smart Chain, Polygon, Harmony, etc. So there's a sort of kind of nuance to how these blockchains execute, but a lot of them kind of have taken Ethereum's lead and just copied what they've done with the Ethereum Virtual Machine. Again, the state transition function, you can think of it atomically as just having a chain, right? Which the nodes and everything on the chain. The state of that chain, basically meaning the database and the storage of what's on that chain, and then new blocks coming in. And the blocks themselves also have to be valid. You can't actually have blocks that sort of break the rules of the protocol. And these rules are basically defined by the Ethereum virtual machines, by the virtual machine. In other words, questions like, if you were to ask yourself, okay, well, what's stopping me as a miner from just giving myself like 1,000 Ethereum when I mine a new block? It's because that new block wouldn't be valid. So all blocks themselves actually have to be valid to be added. The transactions in the blocks themselves could actually fail, but as long as the sort of whole thing abides to the Ethereum virtual machine's execution model, the blocks will be valid and they will be processed and added to the blockchain, and the nodes will sort of accept them as valid blocks. One other thing about Ethereum, just sort of a detail on the execution layer, you also have these things called receipts. So receipts take in the transaction hash of the fully completed transaction, and it will spit out a bunch of values that show you sort of the execution state of the transaction. This is also one thing that makes Ethereum much more readable. as you kind of see, if you actually wanted to get a sort of status update or like a replay on what actually happened with each transaction in Ethereum while it was running, you would have to actually sort of create the whole system and then do sort of like a stack trace on everything that actually happened, which is not very elegant when it comes to actually reading the blockchain, right? One thing they did when they designed the blockchain here is they decided to add in the data structure of receipts, which basically says, give me a transaction hash, I'll find it in whichever block it was located in, and I'll give you, when the transaction actually gets executed, it creates this receipt data structure, stores it in the block for easy access in the future. So that way anyone can just search by the transaction hash itself and see all these other corresponding details with the transaction itself. Again, it makes it really convenient for reading the actual state of the blockchain block through block. You can basically just pick things out instead of having to reset up the whole system and replay it. It makes things just, again, really accessible. Yeah. One other point I've been mentioning, so I've been talking a lot about the Ethereum Virtual Machine. This itself is more of it's a better way to look at things in terms of layers. So on the top level, you have the EVM code. This would be the byte code that's actually executed in sort of the execution environment of the smart contracts and and the logic in that layer. This would basically be your most simplest abstraction of a program running, say, for example, in C++. It would have, you would just be running the code itself in this local execution environment. In the virtual machine layer, you have other things that the EVM will actually worry about, such as the gas left in the current block, the miners in the network, the incoming transactions, et cetera, et cetera. But the EVM holds, on the virtual machine layer, holds things like memory and storage and other things related to sort of the computer rather than just the process that happens at the EVM code layer. And then below that, you actually have the Ethereum nodes themselves. These are pieces of software that are running on the nodes or on the computers across the network. So to not forget for a second, right, these things are actually, these Ethereum nodes are at this level, just computer processes being run across computers that are connected to the internet. So these can either be on your home computer if your computer is fast enough and has enough storage. It can be on AWS. It can be on server farms in offices across the world. It doesn't really matter. All that matters is that the actual process itself or the computer program is running on that computer. And at the very bottom layer, you have the physical layer, which is just the actual CPUs, the hard drives, the physical memory that is being used to run this code. So this is sort of a whole stack and how the thing works. And it kind of gives good context when it comes to picturing how these things actually come together to create a really cool symphony that orchestrates itself sort of automatically. And then one kind of extra slide for the architecture itself. This is just cool if you like computers, specifically if you like computer design as an abstract concept. You can actually look at this itself being everything in this box being the Ethereum Virtual Machine. And then the virtual ROM or read-only memory here is sort of like the disk you would insert into your like Nintendo or like like a CD that goes into your computer that holds the instructions of the transactions that are currently running, right? Or the transaction that's currently running. The EVM here would be sort of like the computer itself with the machine state that processes your transaction. And then to the box on the right, that's the sort of long-term account storage or the world state. In other words, all the state of Ethereum is represented by the state of contracts on the network. Sorry, the state of accounts on the network, right? These accounts are either EOAs with people holding the keys or smart contract accounts that have code and state located at them. So this is sort of a way to give you the details on what's actually going on the computational layer. And then just to cover smart contracts for a bit, because this is actually how you interact with this stuff and make it work and make it run. Solidity itself is a smart contract language that compiles into the EVM opcodes or the byte code. Byte code just being hexadecimal code, like it's just hexadecimal. And then the opcodes themselves are hexadecimal values that are assigned in instruction significance by the EVM specification, such as multiply, add, move, store, load, etc. Solidity itself is a high-level language, so its syntax is a bit similar to C++. the designers actually modeled it after C++ and JavaScript and Python. So it really has actually some of the best features of all three of these languages. And really the only thing you have to worry about is just being a little bit familiar with the EVM and how it works. Once you're sort of familiar with these sort of like high level concepts we covered in these few slides, writing Solidity itself actually becomes quite natural as you learn to understand, some of the native or sort of the raw values, such as the block timestamp, the gas limit of the actual functions, how these things all work, the contract accounts calling between themselves, et cetera, et cetera. So Solidity itself is, again, it's actually quite easy to learn. And we also have the Notion that we have for beginners that covers also how to become a dev, some of the easy resources. One thing we've been recommending this quarter and also throughout all quarters is just to pick up Crypto Zombies, .io. If you want to learn Solidity in a really easy way, it's how I first learned it. It's how a lot of people I knew first learned it. It's a really good way to kind of get yourself familiar without having to run or like write extremely complex things. It's a good starter for like getting into more complex things. And then just another thing, just because we're talking about architecture, the Ethereum decentralized app architecture is run sort of this sort of manner, where you have different computers across the internet running the nodes themselves, or specifically having APIs that connect into the IP addresses of the Ethereum nodes. But they do this all like automatically for you, right? So all you have to do is just like use a library of functions to connect to the Ethereum blockchain. And then you can actually pull data from it or even send transactions onto the blockchain. And by sending transactions onto the blockchain, what I mean is that the functions will take care of the process of connecting to the nodes for you and actually broadcasting the instructions. All you have to do is just worry about just essentially pushing the buttons and writing the right inputs to make the Ethereum virtual machine run as you wish. Cool. One other thing I want to cover, just for an intro on the industry stuff that Kira will be covering, is the idea of the ERC20. I mentioned this a bit before, but the ERC20 name comes itself from the Ethereum request for comments system, which is modeled after the original internet's IRC nomenclature, which is the internet request for comments. Back when they were first developing the internet, they were, it was a very decentralized effort with different universities having their own teams, different research centers, all funded by the government in some sort of manner or one or another. And there needed to be a way to like collaborate when you have a bunch of smart people working on a big project. The bureaucracy can sometimes, or the miscommunication can go on, exponentially. So you need some sort of way to actually, put these things into the protocol that's accepted, or at least widely accepted enough to make it a functioning system. You sort of have a governance structure, right? But it's really not that official. It's more just like people proposing ideas that officially get adopted into the sort of system itself, or the sort of the movement of the technology. But here itself is actually just the overview of the ERC20 standard, the 20th Ethereum request for comments. And it was just to create a token standard because they realized pretty early on that, hey, people, if we solve the issue of a computer that's being run, across all the network, all the nodes across the network, and we have our own native currency, at some point, people are going to come along and they're going to want to create their own tokens, but they're not going to want to actually have to create their own blockchain with all these like instruction sets and like computational models and everything else. They just want to have the logic of this. And we want to give them that logic through a token a token standard, so that in the future, when there's lots of tokens, people can create platforms for them and they'll all adapt to some standard. So this was the sort of idea for ERC20, and now it has been, extremely like popularized, well adopted. It was a very sort of far-thinking thing. Now there's been, like literally tens of thousands of like ERC20 tokens deployed. It's very easy to deploy them themselves, since they're just a template and you just put in the parameters. But there are now thousands of ERC20 tokens that have actual value. They're traded on decentralized and centralized exchanges. You can do a lot of cool things with them. One example being stablecoins, but other examples are, both have happened and are here to come. One other thing is the state model for the ERC20 tokens. So the screenshots now come from the contract itself for the ERC20 template, and then these are just smart contracts deployed for each ERC20 token. And the state here matters because it's actually looking at how these things are tracked on the blockchain. Specifically, the ERC20 contract for a specific token, when it's deployed, has its own address, and it has storage correlated, sort of associated with that address. As a result, you have balances, or what they define here as balances, that actually just tell, it's a mapping, right, that basically stores how much an address has in terms of its own balance, right? So the data types here being the integer balance of an address. So if you have, for example, USDC, a very common stablecoin, the actual address, say if I had an address and someone sent me USDC, it would actually be stored on the blockchain within this mapping itself. And the entry would be my address having now the new balance of the stable coins that someone else sent me. So this is the actual data structure that's being updated when someone sends you an ERC20 token, which is pretty cool. Again, shows you that everything here is programmable and also quite extendable, and so on and so forth. Again, this is just one example of a function, but probably the most important function here, it's the transfer function in the ERC20 token. So if I want to send a stable coin or another ERC20 token to someone else on the Ethereum blockchain, I just take in their address, I send it to someone, I put in the parameters myself. And so these parameters here in the actual function signature, you yourself as an end user of an application wouldn't really have to worry about, since whatever application you're using, like a wallet such as MetaMask, would take care of these things for you, so that all you have to do is just press buttons with your account. But if you wanted to, you could just write your own functions or write your own transactions just from like a library of like a developer library. So you could put these things in manually, and then get access to the most base layer of customizability / expressibility in terms of the code. You can see here, this has a few, it starts off with 2 require statements. It just makes sure that you're not sending money from or to the 0 address, which is a special address in Ethereum that's used as like a burn address, since it would be theoretically almost impossible to generate the private key for an address of 40 zeros, which is the idea why it's used as the burn address. There's a few other functions here, but you can see on sort of the longer line at the bottom, the balance is subtracted from the sender and it goes to the user on the next line, and then an event is emitted, which is another data structure and Solidity that we didn't cover, that another data structure in Ethereum we didn't cover, but essentially it just allows people listening to the blockchain to listen for specific events with parameters and catch them as the blockchain's running. And then it allows them to also not have to run their own nodes. Just for some trivia, the Ethereum nodes right now are around 1.5 to 2 gigabytes. 1.5 to 2 terabytes. So it's about 1,500 to 2,000 gigs. So if you have like a pretty good like laptop, you can run it, but you would most likely need like a sort of desktop or something of that sort. And so for people who have like a normal desktop or just like a phone or something, instead of connecting to, they could connect to other nodes. Yeah, so the idea here is they connect to other nodes and they listen for these events instead of having to actually run the transactions themselves on their own nodes. Right, cool. 2 other things. Yeah.
Why is this so easy?
Oh. Yeah, so the idea here being that when the blockchain started, of course, it was like at 0. And then as blocks started to get added, you had, the blockchain size increased. But the idea here is that in order to get a fully self-verified blockchain, you store the whole global state and you replay it from the beginning in order to get the current state of the blockchain. If you deleted part of it, you would only know the history up until that point, and then anything before it, you just have to trust other people in the network. The idea here is that you actually want a canonical copy or the true copy of the thing from when they exactly started. It's sort of like getting like an